Okay, Algebra 2 kiddos, we are on to Unit 7. And this is all about parent functions and their transformations, and no, not transformations like you see in geometry, for the most part. We've actually already done some of these back in Unit 2, I think, and some of this will come back to you fairly quickly, I hope. It's going to be a short unit, probably 2 weeks and then a test. So it's a very visual, kind of your artistic unit. Okay, so let's start with a parent function. We should already know what that is. We've dealt with parent functions of quadratic equations, linear equations, logarithmic equations, square root equations. And there's some other ones that we want to go on. And really the easiest definition of a parent function is that it is the simplest form of a function. So I often think of it as when you go to get yogurt, go get Froyo. It's your plain vanilla yogurt in a cup before you put all the extra goodies into it. Once you add all those extra goodies, then you have transformed it or translated it into something else. So a translation for our purposes is that whatever you do to your function to move that function either horizontally or vertically. So either left to right or up or down. Okay? Just put a slash in there, that'll be better. Okay, so here, like for example, this is the parent function of a quadratic equation. That's a parabola, right? And we want to describe that function. Well, remember that our vertical shift, which is our up and down, is we have a kind of a parent function that looks like y equals ax minus h squared plus k. So it's always the opposite of what this is our horizontal shift. This is going to shift it left or right by the opposite. And that number that occurs after gives us our vertical shift. Okay, so for this one, we've got a horizontal shift. It's going to do the opposite of what this is because it's whatever gets you back to x. So it has to offset this negative 3. So it's actually moving to the right by 3 and then shifting down 5. So it has a horizontal, actually, yeah, we can go horizontal to the right of 3 and vertical shift down of 5. What you need to remember is within the parentheses, it's always the opposite of what you see because whatever would get you back to x. Here, you're taking the value of all of this and then adjusting it by whatever this number is. So this is exactly what you see. Okay. So let's use a square root function now, and we're going to write a function that includes the translations of a vertical shift up of 5 and a horizontal shift to the left of 17. So that horizontal shift is going to occur within the square root with the x. And since it says to the left of 15, normally your brain would tell you that's negative 17, but it's going to be the opposite of that. So it'd be plus 17. And then it would shift it up 5. So this should look familiar to you. We did a quiz on this. We definitely had a test on this. And this should not be completely new to you. Okay, scale is where we talk about stretching or compressing something. So and we have done this before as well. Okay, so let's think about what happened here. And actually, let's write all of the shifts that this has going on. So in this case, this is our a value, and it tells us how much that is shifting, whether it's increasing by 4 or decreasing by 4. So anything greater than 1, if the a value is greater than 1, because the standard would be 1. When we don't have anything in front of it, that would be a 1. This is stretching. And when the a value is between 0 and less than 1, that's compressing. So when it's a fraction. Okay? So this one is going to stretch by a scale of 4. It's going to have a horizontal shift to the right of 3 and a vertical shift down of 5. On the second one, we have a little bit more interesting situation to deal with because 2x minus 8 can actually be factored out. And what I can factor out of that is the 2. So I would get 2x minus 4 squared minus 5. Now I've got a function that I can tell exactly how much that's being scaled by. So I would have a stretch of 2, a horizontal shift to the right of 4, and a vertical shift down of 5. Okay, so now let's go try and write a couple of functions. So this is our cubic function. Definitely have seen that before. By our vertical shift down of 5 and a horizontal shrink by a factor of 1/3. So that 1/3 is going to come in the front, and that 5 is going to come after. It's not going to be included with the x. It's going to be included after we've already got that value. So f of x would equal 1/3 of x cubed, and then we're going to shift down of 5, so that would be minus 5. So now in the second example, we've got a horizontal shift of 2, horizontal shift to the right of 2, a vertical shift up of 3, and a vertical stretch of 4. So our stretch is going to come in the front. That's going to be a 4. Now we have to deal with this vertical shift to the right. So if it moves to the right 2, it's moving to the right 2, it's a negative 2 within those parentheses because it always does the opposite. And that's cubed, and then we're going to have a vertical shift up of 3. Hopefully this is all coming back to you. This should not be completely new. Hopefully. Okay, and then reflections. So think about a mirror image. When you see yourself in the mirror, what is actually your left arm looks like your right arm in the mirror, but it's because it's a mirror reflection. So this, sorry about that. Okay, so reflections. So we've done reflections before, but typically we have only done them about the y-axis. So we need to talk about the x-axis a little bit. So when we've had our reflections before, we have had them where we've only had them about the x-axis so far. So we've had, for example, a parabola here, and then when we flipped that front number to negative, it flipped it upside down like that. Now we've got to talk about the y-axis also. So the easiest way to think about this is that if y equals f of x, right, we know that those two things are the same. Then if you're looking at your outputs for your functions, if y equals f of negative x, so you plug in the negative input but you get the same output, then it's going to reflect about the y-axis, meaning it's going to flip from here over to here. If your output becomes negative, which is what we've got going on over here, this is what we've typically dealt with, y equals negative f of x, meaning the output just went negative, then that's going to go over the x-axis, which is what we've dealt with so far. So here we have a reflection. And let's describe all the things we've got going on here. So this is our parabola, right? And we know if that a value is negative, then it flips it over the x-axis and makes it go negative. So reflects over the x-axis, or about the x-axis is another way you'll hear it. And it has a stretch of 4, a horizontal shift to the right of 3, and a vertical shift down of 5. These situations you get kind of an interesting thing going on. So right now it would have no reflection. But if I were to factor out of here a -1 so that I had more of a normal looking a, h, and k value. So if I factored a -1 out of here, then I would have x, and I moved it around a little bit, I would have x minus 4 squared minus 5. So this really becomes -2 times x minus 4 squared minus 5. So that tells me I have a reflection about the x-axis again. and I have a horizontal shift to the right of 4 and a vertical shift down of 5. Okay. So here we've got the function. We're going to take an absolute value function, and we're going to have a vertical shift up of 1, so we know that's going to occur afterwards, and it reflected about the x-axis, which means that it's going to flip up this way. So we have f of x equals, the output is negative, and we are going to, sorry, I had a mind blank there for a minute, and shift up of 1, so we're going to add 1. What happens when we're reflecting around the y-axis, we're just changing that to a negative x input. Okay, so we're going to take this same thing. We've got a horizontal shift to the left of 2, which means it's going to be positive 2. Vertical shrink factor by 5. And I reflected about the y-axis, which means my x value is going to go negative. So we should have f of x equals 5. Oh, not parentheses. We've got absolute value going on. 5 negative x, and a shift to the left, which would make it be positive 2 within those absolute value bars. Whoops. There you go. So we've got our stretch or compress. I like to say stretch more than shrink. Our negative input, because it's going to shift about the y-axis, reflect about the y-axis, and then our horizontal shift to the left of 2, which means this needs to be positive 2. Okay, good. Let's do some algebraically now, because graphing is great, but we can't always do that. So let's check algebraically how these are done. And so before we get to that, actually, we are going to go through all of the parent functions, which a lot of these we've already seen before, but we're going to kind of talk about how those will look. So our A value is always our stretch or compress. You can call it shrink if you want. It's fine. I think we know the term stretch and compress at this point. Your H value is going to be your horizontal shift. And that's going to be by the opposite of whatever that number is. Your K value is going to be your vertical shift. Okay. Your B value is going to be if you have a value within the function. So let's look at one of these down here. If you have a factor here in front of the x that cannot be factored out, that would be your B function, your B value. So all we're going to say is the coefficient of x if it can't be factored out. Okay. All right, so let's just do some quick graphing. And we know that all parent functions are going to start at 0. So let's just go with that assumption and let's see what we have. So and you can do quick little charts. So you can do 0, 0, 0, 1, and negative 1. And just see what happens. Use a negative, a positive, and 0 to get your functions. Okay, so 0 squared is 0, 1 squared is 1, negative 1 squared is 1. I've got 3 points I can graph to get a general gist of what's going on. So 0, 0, 1, 1, negative 1, 1, and of course we know that that's a parabola. Another point would be at 2, 4 and negative 2, 4, so there's our parent function for a parabola. Okay, cubic functions, we're going to do the same thing. 1, 0, and negative 1. So 1 cubed is 1, 0 cubed is 0, and negative 1 cubed, you have to be careful, is negative 1. So let's see what that looks like. So we've got 0, 0, 1, 1, and negative 1, 1. If we carry that out, 2 cubed would be 8, so it's way up here somewhere. Negative 2 cubed would be negative 8. So we know that this function kind of has that little curvy thing going on. Remember what we talked about before when we were doing functions, that whatever the degree of the function is how many changes of direction it makes. So if we check that with this, it changed twice. It went down then up. Here we go up and then over and up. Absolute value function looks very much like a parabola, except it's much straighter. And the parent function, so the absolute value of 0 would be 0. Absolute value of 1 is 1. And the absolute value of negative 1 is also positive 1. So the only difference with absolute value functions, it's very much a V-shaped shape because it's just taking the opposite, always the positive of that function. So until there's a negative out in front of that, you're going to have nothing down in quadrant 3 and 4. Everything's going to be in quadrant 1 and 2. So an absolute value function looks like this. Until we start messing with it, it's a V at a perfect 45-degree angle. Slope of 1, slope of -1. Okay, square root function is kind of an interesting thing. So square root of 0 is 0. The square root of 1 is 1. So now think about, can you take the square root of a negative number? You can't. So all of this has to stay within quadrant 1. So let's do another one. So square root of 4 would be 2. So there's 3 points that we can graph. We have 0, 0, 1, 1, 2, 3, 4, and 2. So that's our little square root function that we've done before. So until we adjust it, all of our square root function is going to be only in quadrant 1. Let's put that on there, quadrant 1 only, because we can only have positive inputs. And for graphing purposes, you only deal with the positive outputs. I do recognize that like the square root of 4 is also -2, but for graphing purposes, you're only using positive inputs and positive outputs. Okay. Down below each of these functions that we're doing, you can see how the a, h, and k are applied as well. Okay, exponential function. So again, let's just use our 3 quick little numbers that we have. So 2 to the first would be 2. 2 to the 0 power, well, 2 to anything to the 0 power would be 1. And then 2 to the -1 power is the inverse, or sorry, the reciprocal of what we got up here. So that would be 1/2. So I've got 1, 2, 0, 1, and -1, 1/2. And we know that our exponential functions look something like this. And they always kind of cruise the x-axis, but they will never touch because there's no number we can put in to get an output of 0. It just cruises along that line right there. This should sound somewhat familiar. So logarithmic function is the inverse function of an exponential function. So we could actually take these 3 inputs and just flip them. What was an x now becomes a y. So we would have 2, 1, 1, 0, and 1/2 -1. So we'd have 2, 1, 1, 0, and 1/2 -1. So we look and see what that does. It cruises along the y-axis and never touches for the same reason. Remember that exponential functions and logarithmic functions are the inverse of one another. Okay, greatest integer function is kind of an interesting thing. They're also called a piecewise function. And we'll discuss this one a little bit more in class. I just want you to kind of get down what it looks like. And it's kind of I'm going to use a different pen here so it's a little bit clearer. You may have seen these in a textbook and thought, what the heck is that? So they look something like this. They're also called piecewise functions. And they're actually not that difficult, but I would like to kind of go into a discussion of that in class, and I think it make more sense. What it means is, for whatever your input is, what is the nearest integer without going over? So let's use an example. So if I asked you, okay, the input is 4.5. Well, the nearest integer to 4.5 without going over 4.5 would be 4. Let's pick another one, 4.8. Well, if I put in that, what's the closest integer to 4.8 without going over 4.8? It's kind of like the Price is Right of graphing, actually. As close as you can get to without going over. So if I did that, my input is 4.5, so 1, 2, 3, 4.5. I'm going up here to 4, but I can't get over 4. We go 4.8, I'm still here. At 5, if I got up to 5, it would jump now. What's the nearest integer to 5 without going over 5? Well, that's obviously 5, so then you skip up to the next step. Okay, we'll discuss that a little bit more in class. Okay, last one, rational functions. So we have 1 over 1 would be 1. 1 over -1 would be -1. Oh, now 0 is a problem. Can I put 0 in for here? 1 divided by 0 is what? That's undefined. So your x value cannot be 0. So let's plot the points that we have. We have 1, 1, and we have negative 1, negative 1. And if you remember, this is the unit we just got done doing, unit before last. They're rational functions, and it's kind of a split function that looks like that. Okay, so graph the following at the bottom, using a table of values to help out if necessary. And I don't even know that we need to have a table of values because now we're pretty good about our shifts. So why don't we do this? Why don't we take our parent function, and that's a square root function. So let's use inputs of, let's make it easy. We have an input of 0, and we'll graph our parent function, and then we'll graph the shift. So parent function is just square root of x, okay? And if we tell ourselves what we've got over here, we have, well, let's graph it first, sorry. Let's do that, and then we'll get over to this. Square root of 0 is 0. Square root of 1 is 1. We can't do square root of negative 1 because we can't take the square root of a negative. There is a square root of 2, but it's a decimal, so I don't want to deal with that. So I'm going to use perfect squares because to me that's a lot easier. Okay, so then I'm going to use square root of 4 is 2. So if I were to just graph those points, I would have 0, 0, 1, 1, and 2, 3, 4, 2. And that's my square root function that we've dealt with before. So now I'm going to adjust those a little bit. And I'm going to go ahead and use my same inputs of 0, 1, and 4. And I'm going to give myself a little room to work there with negative 2 square root of x plus 1 and negative 3. And see what my outputs are over here. Okay, so for 0, I've got negative 2 times the square root of 0 plus 1, which would be 1, minus 3. So that's going to give me an output. Let me fix this a little bit. That's going to give me an output of square root of 1 is 1 times negative 2 is negative 2, minus 3 is negative 5. And negative 2 times the square root of x plus 1. Ooh, that gives me an ugly number. I don't know that I like that. Minus 3. So that's going to give me a 2. Maybe I'll change my input after all. So what would give me the next perfect square? I could actually put a negative 1 in here, couldn't I? Because that would give me a 0. So I'm actually going to change this to a negative 1. Let's see what happens. So negative 1 plus 1 is 0. That helps me. Square root of 0 is 0 times negative 2 is 0. Minus 3 is negative 3. So we're going to see, I want you to keep these numbers in mind. And the 4 I don't think is going to help me, but a 3 would help me here. Because 3 plus 1 is 4. And I can take the square root of that because it's a perfect square. So square root of 4 is 2 times negative 2 is negative 4. Minus 3 is negative 7. So now I've got 3 points that I can graph. So I've got 0, 5, negative 5, 1, 2, 3, 4, 5. And I've got negative 1, negative 3, 1, 2, 3. And I've got 3, negative 7. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7 would be way over here. So look what that is doing now. It's actually, it reflected it and it shifted it over everything to the left 1. My original point was here, my new point is here. So it shifted it to the left 1, down 3. If I look at my different points that were reflected, that one got shifted down 1, 2, 3, and that negative 2 caused a reflection. Okay, we're going to do lots of matching and moving and translating things in class. So that's it for section 1.